In this PowerPoint, we will study autocorrelation, that is first order autocorrelation, and heteroskedasticity. These are properties of disturbances. In this model, the error term ET is serially correlated, as you can see from equation 2. ET is equal to phi ET minus 1 plus Vt, where Vt, however, is serially uncorrelated. That is, Vt is uncorrelated with its past or future values. This model is called a model of first order autocorrelation. Why does serial autocorrelation arise? Typically because of two reasons. One, because the regression equation is misspecified, or two, because of seasonality in the data. How does serial autocorrelation arise through misspecification? Look at the following diagram. On the y-axis, we have per capita agricultural output across various districts in a country. On the x-axis, we have annual rainfall in each of these districts. Now it is possible that as annual rainfall increases, per acre output increases up to a point and then falls. So the relationship between per acre output and annual rainfall is not linear, as you can see in the scatter diagram. However, suppose we specify a linear relationship given by the red straight line. You can then see that all the points in the blue circle above the red line will be positive, whereas all the points in the red circle below the red line will represent negative error terms, which means that if a given error term is positive, it is likely that the error terms immediately next to it are also likely to be positive, and if a given error term is negative, it is likely that error terms immediately around it are also likely to be negative, which will induce a correlation in the error term. So if we know that a given error term ET is positive, you would expect ET plus 1 also to be positive, whereas if you expect ET minus, if you know that ET minus 1 is negative, you would expect ET to be negative as well. Another reason for serial autocorrelation in the error terms of a regression equation is because of potential seasonality in the data. In the graph below, let y-axis represent sales of a particular commodity in month I, whereas on the x-axis we have price of the commodity in that particular month. Overall, as you can see, the relationship between them is negative. But suppose every 6 months, the sales of the commodity are particularly high relative to the linear regression line. So every 6 months, you would expect the error terms to be positive, which means that if ET is positive, ET plus 6, ET plus 12, ET plus 36 are all expected to be positive. This means that you have seasonal correlation in the error term, which can induce serial autocorrelation. What is the impact of autocorrelation in the error term? A. Despite of autocorrelation, the OLS estimator for beta hat will continue to be unbiased and consistent. Remember, unbiasedness or consistency are not possible only if the correlation between x and the error term is not equal to 0. Here, x is not correlated with the error term in model 1. It is the previous values of the error term which are correlated with their future values. So the correlation is in the error term itself and not between x and e. Therefore, the OLS estimators continue to be unbiased and consistent. The problem is that the variance of beta hat OLS is no longer sigma square upon summation xi minus x bar square as it would have been had the correlation between error terms been equal to 0. So why does autocorrelation matter? The OLS estimators will continue to be unbiased and consistent even if there is heteroskedasticity or autocorrelation. However, in the case of autocorrelation or heteroskedasticity, the usual standard errors of beta hat OLS, that is sigma square upon summation xi minus x bar square, will be incorrect. Hence, hence the t values based on the usual standard errors will also be incorrect. So what does one do about this? One strategy is to transform equation 1 in such a way that the error terms in the transformed equation are no longer serially autocorrelated.
So this will take us to the generalized least square model, where the generalized least square model is actually the linear regression model with an impact on the OLS.
Transforming the model so that it satisfies the assumptions of the OLS, that is, the error terms are neither heteroskedastic nor autocorrelated, and then doing a regression on the transformed model is called the method of generalized least squares or GLS. So how does one achieve this? Think of the usual model. Yt is equal to alpha plus beta xt plus et, where Et is now serially autocorrelated. That is, Et is equal to phi Et minus 1 plus Vt. There are two things to remember about this equation. The absolute value of phi is strictly less than 1. Secondly, the error term Vt in the equation for Et is serially not correlated. That is, we are going to explicitly assume that Vt is normally distributed with mean 0, a constant variance sigma square V, and the covariance of Vt with its past or future values is 0. Now since Et is correlated with Et minus 1, in this specific case, we say that this model has first order serially autocorrelated errors, or the errors follow an AR1 process. The point is to transform this model into one where the errors are not serially correlated. So consider equation 5, which is nothing but equation 1 lagged by one period. That is, if equation 1 had yt on the left hand side, in equation 1 had yt on the left hand side, equation 5 has yt minus 1 on the left hand side. So we have yt minus 1 is equal to alpha plus beta xt minus 1 plus et minus 1. Now consider multiplying equation 5 by phi. Here we are assuming that we know phi. So we have phi yt minus 1 is equal to alpha phi plus beta phi xt minus 1 plus phi et minus 1, which we will call equation 6. Now subtract equation 6 from equation 1. So on the left hand side, you have yt minus phi yt minus 1. On the right hand side, you have alpha minus alpha phi plus beta xt minus phi beta xt minus 1 plus et minus phi et minus 1. Now note that et minus phi et minus 1 is indeed Vt. We will call this transformed equation, equation 7. Now, equation 7 in the previous slide or equation 8, which is just equation 7 written more neatly, has an error term that is not serially autocorrelated. This is what we wanted to achieve. We wanted to transform equation 1, which had serially autocorrelated errors, into a new equation which now no longer has serially autocorrelated errors, so that we can apply usual OLS and the usual OLS standard errors, and the t-values will be applicable. But there is a critical assumption here. In order to transform equation 1 into equation 8, we need to know the value of phi. But in reality, we are unlikely to know that value. So we will have to find a way to estimate it. In other words, we will have to find a way of making our GLS method feasible. Hence, what we are looking for is a feasible generalized least squares estimator. How does one achieve this? We will break the process into two steps. In step 1, we simply estimate regression 1. Remember, our estimates of alpha hat and beta hat, even from model 1, are unbiased and consistent. So we can go ahead and estimate model 1. After you estimated model 1, get y hat t, which is equal to alpha hat plus beta hat xt, and obtain e hat t, which is yt minus y hat t. After you've obtained E hat t, then do the regression of E hat t is equal to phi E hat t minus 1 plus Vt. Remember, this is a regression equation without an intercept, and hence the estimate of phi hat is given by summation E hat t minus 1 upon summation E hat t minus 1 square. So the idea is to estimate the value of phi and then substitute it into equation 8. So instead of yt minus phi yt minus 1, we have yt is equal to phi hat yt minus phi hat yt minus 1. Instead of alpha into 1 minus phi, you have alpha into 1 minus phi hat, and so on. So you replace the unknown phi with an estimated phi hat. Then we go on to form the feasible generalized least squares estimator beta hat FGLS in the usual OLS format. The new dependent variable is y star t. So, and the new independent variable is x star t. And therefore the beta hat FGLS is given by summation y star t minus y star bar into x star t minus x star bar upon summation x star minus x star bar for the whole square. The important point was not really estimating beta hat and alpha hat, because there was no problem with the OLS estimators anyway. The OLS estimators, as we saw, were consistent and unbiased. The problem was obtaining correct standard errors. Now here, that is the key. So the variance of beta at FGLS is now sigma hat square V upon summation x star t minus x star bar the whole square, and this is the estimated variance of the beta hat FGLS. How does one find sigma hat square V? You take y hat y star hat, these are estimated values of y star, minus each value of y star. Sum the gaps. How many gaps do you have? N minus 1, because we have lost one observation in taking a lag. And then divide this sum by n minus 3. Why n minus 3? Because we had n observations, we lost one observation to the process of taking a lag, and then we have two parameters that we have estimated. So the degrees of freedom here are n minus 3 if we had initially in model 1 n observations to start with. So consider model as usual, yi is equal to alpha plus beta xi plus ei. But when we assumed homoskedasticity, we said that the variance of each of the error terms ei was constant. So we said variance of E1 is equal to variance of E2 is equal to variance of E3 and so on, and which was correct, all of them were equal to sigma square. But now we're going to make that a change in that assumption. We're going to assume that each of the error terms have a different variance. So we're going to allow variance of E1 is equal to sigma square 1, variance of E2 is equal to sigma square 2, variance of E3 is equal to sigma square 3, and so on. And potentially, we're going to allow each of the sigma square i's to be different. So under heteroskedasticity, we allow each of the error terms to have a separate variance. So the variance of E1, which is sigma square 1, could be different from the variance of E2, which is sigma square 2, which in turn is different from the variance of E3, which is sigma square 3, and so on. This graph represents one particular type of heteroskedasticity where the variance of the error term increases with the value of x. You can see in the picture that as x increases, the spread of the data expands. That is, the variance of the error term is not constant, but actually is some function of x. So just as in the case of autocorrelated disturbances that we have seen before, the OLS estimators, despite of heteroskedasticity, continue to remain unbiased and consistent. That is because X and E are still uncorrelated. And just as it was the case under autocorrelated disturbances, the impact of heteroskedasticity is in changing the formula for the variance of beta hat OLS. The variance of beta hat OLS is no longer sigma square E upon summation xi minus x bar square, but will now have to be changed. So then we can take two approaches to the problem. In the first approach, we allow the error term in equation 1 to continue to be heteroskedastic in the sense that the variances of all the individual error terms are not identical, and then we can modify the formula for the variance of beta hat to accommodate this feature, which will give us the standard errors which are consistent with heteroskedasticity, which are also referred to as heteroskedasticity consistent standard errors. The other approach is the GLS approach, which consists of modifying equation 1 in such a way that the error terms of the modified equation no longer have heteroskedastic disturbances, but in fact each of the error terms of the modified equation have identical variances. So think of equation 1 again, yi is equal to alpha plus beta xi plus ei, but now each of the ei's has a different variance. So variance ei is sigma square I for each I. Now let's make a heroic assumption. Let's assume that we know each of the sigma square i's. I know this is unlikely, but currently let's go with it. So let's divide yi by sigma I. So we have yi upon sigma I is equal to alpha upon sigma I plus beta xi upon sigma I plus ei upon sigma I. Let's redefine the variables. Let the new yi star be yi upon sigma I. Let alpha star be alpha upon sigma I. Let x star I be xi upon sigma I. And let the new error term vi be ei upon sigma I. So what we have done is we have actually transformed the data. Now let us see whether it solves the problem of heteroskedastic disturbances. Well, the problem was that the variance of the error term in model 1 was not constant. So the problem would go away if the variance of the error term in the modified equation is constant. So let us find out what is the variance of Vi. Now Vi is Ei upon sigma I. You know that variance of x upon alpha is 1 upon alpha square variance of x. So by the same token, variance of Ei upon sigma I would be 1 upon sigma I square variance of Ei. But the variance of Ei is itself sigma square I, so you would have 1 upon sigma square I into sigma square I, which is 1, which means that the variance of each of the error terms would be 1 and hence constant. Therefore, the problem seems to have been solved. So the beta hat GLS uses the formula that the OLS uses, except that instead of using the original variables xi and yi, we use the transformed variables xi star, which is xi upon sigma I, and yi star, which is yi upon sigma I. So therefore, beta hat GLS becomes summation xi star minus x star bar into y star minus y star bar in the numerator and summation xi star minus xi star bar square in the denominator. You can always rewrite it in the form of the original x's and y's, which you can see in the blue color, where instead of xi star I've just used xi upon sigma I. Instead of x star bar I've used summation 1 upon sigma I into xi, the whole divided by n. Similarly, for y star I've used yi upon sigma I, and for y star bar I've used 1 upon sigma I yi, the whole summation upon n. The beta hat GLS estimator in this case is also called the weighted least square estimator. Why is it called that? We will soon see. So consider the original model yi is equal to alpha plus beta xi plus ei. We assume that we know sigma I, and so we divide yi by sigma I. So we have yi upon sigma I on the left hand side and alpha upon sigma I plus beta xi upon sigma I plus ei upon sigma I on the right hand side. As you can clearly see, because ei upon sigma I is nothing but vi, the equation in the previous slide can be written as summation vi square is equal to summation yi upon sigma I minus beta xi upon sigma I the whole square. We can take out sigma I square common. So you get summation 1 upon sigma I square yi minus beta xi square. Y minus beta xi square is nothing but the squares of the residuals of the original OLS equation. All that is happening is each of the sums is being weighted by the reciprocal of the variance of that particular error term. So error terms which have a large variance actually get a relatively smaller weight in calculation of beta hat GLS, while the error terms which have a relatively smaller weight actually get a higher degree of importance in calculation of beta hat GLS. In the OLS model, all the error terms have the same weight. You minimize summation ei square. Whereas for the GLS, we minimize summation 1 upon sigma I ei square, where sigma 1 upon sigma I square ei square, where each of the sigma I square gives you the variance of that particular ei square. So each of the squared errors is weighted by the reciprocal of the variance of that error term, and this weighted sum is what we minimize in weighted least squares, which is nothing but the GLS estimator in this case. Fine, so if you know sigma square I, you can always do this. But the question is, we don't know sigma square I. In fact, we are not likely to ever know it. So how does one then use all this? So what we'll do now is we will make a strategy for estimating sigma square I for every I, and then we will use the estimated sigma square I in place of the original sigma square I to develop a feasible generalized least square. So let us start by specifying the variance of EI as some function of a set of variables called Zi. Now these Zi could be some external variables. They could also be nothing but the variables xi which are included as independent variables in the regression equation. More particularly, let us assume that sigma square I takes the form of E being e raised to theta plus gamma xi, where xi is the explanatory variable in our regression model. Instead of this xi, it could have been any other variable zi. It could be e raised to theta plus gamma 1 z1 plus gamma 2 z2 and so on. But for simplicity, we are using e raised to theta plus gamma xi. Now, if you take natural logs on both sides, then we have natural log of sigma square I is theta plus gamma xi. So start with estimate the original equation in untransformed variables. The original equation was y is equal to alpha plus beta xi plus ei. We know that because x and e are uncorrelated, OLS estimators will continue to be unbiased and consistent. So use OLS on the original equations and obtain alpha hat, beta hat and e hat I, which is yi minus y hat I, which is yi minus alpha hat plus beta hat xi. Step 1, estimate yi is equal to alpha plus beta xi plus ei. Obtain alpha hat, beta hat and e hat I. You know this can be done because alpha hat and beta hat will continue to be unbiased and consistent estimators because the covariance x and e is still assumed to be 0. In theory, of course, each of the e hat I squares can be used as an estimator for the sigma I square. However, this will not be a very good estimator. The reason is, as the sample size increases, you actually have more and more values of sigma I square to estimate, which means that as the sample size increases, the number of parameters that you have to estimate also increases. On the other hand, for consistency, we want the sample size to increase, but the number of parameters that you estimate to remain the same or not increase as fast as the sample size. Therefore, because each of the e hat I squares is being used as an estimator for sigma square I, if you have n observations, you have n sigma square i's to estimate. If you have n plus 10 observations, you have n plus 10 sigma square i's to estimate. Obviously, the estimators cannot be consistent. So this is where the parameterization log sigma square I is equal to alpha plus beta xi helps. In this parameterization, we have only two parameters to estimate, alpha and beta. Once alpha and beta can be estimated, then you can form estimates of log sigma square I by plugging in the appropriate values of x in the regression equation. So the point is the number of parameters to be estimated drops from n to 2. Now, as the number of observations increases, the number of parameters relative to the number of observations will keep on going down, and therefore, because you have additional information coming in, the estimators will become consistent. So the point is, once you obtained log of e hat I square, then you regress the log of e hat I square on gamma theta plus gamma xi, where xi is a dependent variable. We obtain estimates of theta hat and gamma hat from the usual OLS regression and get log of e hat I square hat, which is the estimated value of log e hat I square, from which we use these values to find an estimate of sigma hat I square, which it can be obtained by e raised to log of e hat I square estimated values. So you raise the left hand side of theta hat plus gamma hat xi to E and obtain estimates for sigma hat I square. With this step, we are almost there. Now that we have sigma hat I squares, they can be used to transform the variables xi and yi. So instead of having xi upon sigma I, we do xi upon sigma hat I, which is xi star. We do yi upon sigma hat I, which is yi star. And then we we use these variables to do the original regression and obtain beta hat FGLS and alpha hat FGLS.